So today what we're going to talk about is solutions, and this is part one of a two-part video series. The other part can also be found on YouTube. So what we're going to look at is dissolving stuff in stuff, and in order to understand how that happens, you need to know why things dissolve. It's the principle underlying most dissolving is like dissolves like. Things need handles, or they're loosely associated. In other words, if I dissolve a salt in water, I have to have a handle. I have to have some sort of electronic charge for that water to reach out and grab that. And so to the right I have different intermolecular forces that provide handles between the solvent and the solute. And I don't want you to forget that our weakest force is the London dispersion forces, or van der Waals forces. And even though those attractions may be weak, you can make up for that by having multiple points of attraction. So starting at the lowest energy, the van der Waals dispersion forces, up to the more stronger intermolecular forces such as hydrogen bonding, and then of course ion dipole. So some of the terms: a solution is a homogeneous mixture. Although this is the more technical term and it refers to what in chemistry we call a solution, a lot of times the term solution is loosely bantered around as anything dissolved in a solvent. The solvent is the predominant phase. So in the case of salt water, it's the water. The solute is the less dominant phase. It's what's being dissolved. It's, in the salt water case, it's the salt. In solutions, individual molecules are dispersed throughout solvents by intermolecular forces. So one of the underlying ideas about a true salt solution is that the solute is distributed evenly throughout the solvent. So when individual forces get weak, the mixtures are sometimes referred to as a suspension, and you may have clumping in that case. And it's not a true solution. So when things dissolve, there's lots of interaction. Then some properties will change depending on the number of solid pieces present. If there's very little interaction, properties of the solvent may not change at all. One of the things you'll see when things dissolve is that heat is evolved or released. And if there's lots of interaction between the solute and solvent, usually there's going to be a change in the colligative properties. And colligative properties are basically changes in the solution depending on how many solute parts are involved. These involve boiling point, freezing point, osmotic pressure, vapor pressure, and conductivity. And I've boxed these two because they are unique in how they depend on the structure of the solute. So lots of interaction. Let's talk about salt dissolving water. This is a good model to explain a lot about dissolving. So here's actually my water molecules. And when I dissolve the salt, polar ends of the water, the slightly positive end where they've lost electrons in the poles attaches to the anion chloride, and then the negative end where the electrons have shifted over in this covalent bond, that attracts to the positive sodium ions. And if there's enough of them, because these dipoles are actually weaker forces, if there's enough of them, they can gang up and actually start to rip this ionic bond apart. And this intermolecular bond is a lot stronger, but you can gang up with enough waters and break it free. And that's really the process of dissolving. But you have to have handles. That's one of the keys here. Once it's dissolved, water will continue to surround it until it's completely hydrated, or it's in a solvent shell. And whenever this dissolving event happens like this, where there's a strong interaction, there's definitely going to be heat involved. And there's going to be heat involved for three different reasons. One is you have to split the solvent apart. The second thing that happens is the solvent literally has to start splitting the intramolecular bonds apart, or break the lattice bonds. And the third thing is bonds are reformed. They're weak bonds between the hydrogen dipoles and the ion. But anytime bonds are broken, it's going to cost you energy, and anytime bonds are reformed, it'll release energy. So if you want to look at the solution enthalpy, and enthalpy and energy and heat are sometimes used interchangeably, you have to consider the energy it took to break apart the solute, the energy to break apart the solvent, and then the energy that's actually released when the new solid particles in the solvent are recombined. Sometimes these two enthalpy quantities together are considered the heat of hydration. So heat is released or required when something dissolves. So we'll look at salt dissolving water as our model here. But in order for something to be exothermic, in other words, the entire heat of solution feel hot to you, it'll release energy, then the things that require energy, that are endothermic, solvent separation and solute separation, combined are less than the heat released when the hydration occurs. And this is considered an exothermic solution. And when we get to the numbers part of this, when we actually do calculations, that's going to have a negative sign attached. Doesn't mean that it's less than zero, it basically just shows direction. And when you see the negative sign, it means it's leaving the reaction. Or if you grab that reaction up in your hands, if it's taking place in a vessel that you were holding, it would feel hot to you. Here's an example of an endothermic reaction where actually the breaking events, the solvent separation, solute separation, the energy involved for those is greater than the energy released when the solvent covers the solute. And this will be an endothermic reaction, and the sign on that number will be positive. An example of this is dissolving sodium hydroxide in water, commonly found in oven cleaner. An example of this is ammonium nitrate. And this is the chemical that you see in these cold packs sometimes, where you snap them and this salt is released into water and it actually feels cold. It pulls energy from its surroundings to make this reaction take place. Okay, so if you want to actually do calculations, you can look up these lattice energies, etc. But to just kind of know this intuitively, I just want to remind you why the lattice energy changes. It's all based on Coulomb's law. And a reminder, once again, Coulomb's law is charge of fluoride ion, and I got a lithium cation. And so the charge of the lithium and the charge of the fluorine multiplied by each other times the constant divided by the distance between these two charge centers squared. So if the distance between the two charge centers is large, then that means that energy holding them together is actually lessened. And if the charge is increasing, that would mean the energy holding them together, the lattice energy, would be great. And this is shown in this example where we basically combine lithium to a set of halogen ions that are increasing in size as you go down the periodic table. So when you take lithium fluoride, the two smallest ions, and you combine them, that's going to make that ionic radius very small. Then the energy that holds them together is great. And then as you start to increase in size, bind lithium to chlorine, then to bromine, then an iodine, the distance is getting greater. So the energy holding them together drops off. And that trend holds true through the periodic table here. Here's another look at that same sort of table, but just to point out something else, and that is another comparison can be made in terms of charge. So in this case, let's compare something that's held together by +1 charges, lithium and fluoride, and that has a lattice energy of 1047 kilojoules per mole. Once again, the negative doesn't make it smaller, it just is showing the direction. And then you can compare that to something that's +2 charge, the magnesium ion and the oxide ion, and see how the lattice energy is increased. And then if you go up to an aluminum ion, which is a +3 ion, it's increased 5 times again. So charge and size are what can control lattice energy, and those are periodic trends. So as far as the water reattaching to the ions once they've been broken up, what we call hydration, this is an intermolecular force. Same rules apply. You're trying to hydrate smaller and smaller ions. So starting here with cesium, the ionic radius is very large, it's low on the periodic table, and you go into smaller and smaller ions. Then the heat of hydration, the heat energy released whenever these things hydrate, is greater. And the same trend applies when you jump up. So let's just compare, for example, a sodium ion to a calcium ion, which are very close in ionic radius. But the difference is calcium is a +2 charge. And look at the large increase in hydration energy. Once again, this is all based on Coulomb's law. So trends in ionic hydration, once the water is broken apart You're talking about the energy released when new bonds are formed to the ion. Okay, so let's talk about the colligative properties. Let's talk about how the properties of the solvent, what it's being dissolved in, how it changes when you start to dissolve stuff in there. So we're talking about how the properties of water change as we start to dissolve sodium in there. And I just want to remind you again of what boiling is, that basically what happens in boiling is some of these water molecules actually have enough energy. They can literally break free from the water and go into the vapor stage. That's what boiling is. So how does that change when there's actually a salts present? With salt present, water can bump into and lose its energy to the salt. And once it absorbs that energy, you're going to have to get more energy in order for this molecule to evaporate. And that's what happens in boiling when you have salt present. So now it's a colligative property because it doesn't matter what's present. It doesn't matter if it had been a chloride ion or it had been a fluoride ion. It doesn't matter about size. It just matters that it's dissolved and interacting with the water. And it will always raise the boiling point. Adding a salt to a solvent never lowers the boiling point. It always raises it. Okay, using the same idea, you might also think about this in terms of vapor pressure. Same principle applies. You know, in vapor pressure, you just have a small percentage of these molecules that just have enough energy that they can vaporize. But that number is lower when salt absorbs some of the energy from those salt molecules. And that's provided that the solute has less vapor pressure than the solvent. So you want to keep in mind that this is a little bit dependent on the solute that you've chosen. What about lowering the melting point? How does that happen? We're talking about things from a qualitative standpoint. In the next video, we'll really try and put numbers on this. But whenever you're melting something or you're freezing something, so in this case, we're going to talk about water. The water starts to bind through hydrogen bonding. It bonds in this, it's very open, structured network. And that's what we call ice. So it's fairly intuitive to consider that if you have water trying to form in the presence of salt, there might be ions present disrupting that formation. So now what we have to do is we have to take the energy of both the salt and the water down enough that these can slow down and settle in close enough that they can start to form these weak intermolecular forces and make crystal lattices. So once again, it doesn't matter what's present as long as it disrupts the bonding of the solvent, and it will always lower the melting point. So water usually melts at 0 C, salty water melts at below 0 C. And that's why you salt the roads during the winter, to get the ice off. And melting point, once again, is independent of atom identity. The next colligative property is something called osmotic pressure. So in order to understand osmotic pressure, I'm just going to put water in this U tube. And I've blown up some of the molecules so you can see them. And then you place a membrane in there that is able to pass the solvent but not the solute. Now this may seem like a kind of a exotic setup, but it really is relevant to things we know because our cell walls work this way. They're able to pass solute or solvent back and forth, but they prevent the passage of some ions. Okay, sometimes this may be the internal cell content, or this might be the internal cell content, and this will be the outside of the cell wall. But basically then, if you get one side of this membrane a little more salty than the other, and once again it's a colligative property, so it doesn't have to be a salt, it could be anything that dissolves in the water, osmotic pressure starts to build up, and there's a natural tendency for this fluid to flow in and try and dilute down these salts. So the water will pass the membrane, trying to dilute that down, and the level will come up on this side. And that difference in height actually represents the osmotic pressure. But another different ways to consider this osmotic pressure is the force that forces this fluid through the membrane. Or another way sometimes it's stated is, in order to prevent this water from flowing, how much pressure would I have to put on this backside? Any of those is how you would measure that osmotic pressure. Another colligative property is conductivity. And I just want to explain conductivity a little bit first. So my idea is to basically wire up this battery in such a way that it passes through the solvent and makes a connection with this light. And once I complete the circuit, if I'm able to flow electrons through this entire circuit, you're going to see this light up. So if I just start with water alone, and here's my negative lead over here. So basically that means that electrons are being moved out of there. Polar water isn't able to transfer charge. This is a full electronic charge. Polar water is just a slight shift of electrons. So polar water is actually an insulator against electricity. So pure water would not conduct electricity. So now what happens when you put salt in there? How do things change? Same process. Okay, I'm over here generating electrons at the anode. Electrons start to build up. The sodium ions migrate over to this lead, which is negative. And if electrons are flowing away from here, and this actually has chemistry in here that are gaining electrons, undergoing a reduction, then you're going to actually see the chloride ions migrate over to this pole. So then the next step that occurs is there's actually a transfer. The electrons are picked up by these sodiums. They become sodium 0. So they basically are reduced. And once that happens, to charge balance this system, these chloride ions, they actually lose their electrons to this pole, which is positive, become chlorine molecules. And then that buildup of electrons there actually flows through the circuit back over to where electrons are building up. And the flow of those electrons is what turns on the light bulb. So that electron doesn't necessarily flow through the battery. This battery is creating electrons on this side and it's sucking in electrons on this side. So it's undergoing oxidation chemistry inside here, creating electrons, and reduction chemistry on this side, gaining electrons. But that's for another YouTube talk. So if we put this all together and get this thing in motion, once again the sodium's going through reduction, chlorine's going through oxidation, batteries producing more electrons to take up, sucking in the excess electrons. The anions and cations are moving to the respective poles and then undergoing reduction cations. So there's actually atoms building up on both of these leads during this process. But the continuous flow of electrons is what creates electricity. And so long story short, this particular solution is able to conduct electricity in this manner. And so it's a measure we call conductivity. And so electricity needs ions to travel on. And dissolved salts are called electrolytes. In other words, dissolved ions, dissolved charges in solution are called electrolytes. And that's reserved for those. Strong electrolytes are things that dissolve easily and make ionic charge, like sodium, chloride, or zinc nitrate. Any of the nitrates or halide families are traditionally good at dissolving. Weak electrolytes are things that, even though they're ionic in nature, they don't dissolve very good. So they're fairly insoluble, like hydroxides or carbonates. So when you drop these in solution, they don't make calcium plus ions. It stays together as a molecule. These are poor at conducting electricity because you need that free ionic charge. And then there's non-electrolytes. These things don't form ions at all. They are things that are bound into water because of hydrogen bonding or just dipole bonding, even though they're very soluble. And stuff like sugars, for example, they'll dissolve in water, but they're non-conductive. In order to figure out how the colligative property is going to change, you need to count the parts. And once again, we'll do more math on this later, but I want you to give you this qualitative feel about this. So we're going to take the example of glycerol, and here's the structure. You can see it has a lot of hydrogen bonding in there. There is 1 mole of solute for every mole of solid you dissolve in water. So 1 mole of glycerol gives you a 1 molar solution roughly. And the water hydrogen bonds to it. But when you dissolve sodium chloride, it has 2 moles of solute per mole of solid, because the sodium chloride breaks up and you get a sodium ion and a chloride ion. And here's another example. Iron 3 chloride, dissolve that. Now you get 4 moles of solid per mole of solid dissolved, because you break out the iron 3 ion and 3 of the chloride anions. This will change the melting point, boiling point, osmotic pressure, and vapor pressure, so it's going to have lower changes, less changes. We'll get the exact numbers in the next video than the one that has 2, and that's going to be less than the one that breaks up 4. So if you can put in more molecules per mole, that's going to give you more bang for your buck, so to speak. But I do want to remind you, when it comes to conductivity, glycerol does not apply because it doesn't free up ions. Sodium chloride and iron 3 chloride would also have corresponding increase in conductivity because there's more parts free in there. So solubility does matter, as I stated earlier. So here's HCl, 2 moles of solute per mole of solid. Here's sodium chloride, same thing, 2 moles per solute per mole of solid. They're both very soluble, so in all colligative properties, these are equivalent. But here's silver chloride, 2 moles per solute per mole of solid. But silver chloride, as you may remember from your solubility rules, is insoluble. So when you dissolve it, it stays together, and you don't have free ions, and they are not interacting with the water. So it has no effect on the colligative properties, except for what little bit disassociates. We'll talk about that later in the equilibrium section. So in this case, the changes in colligative properties would be the same between these two species, assuming that they're at low enough concentrations they both are totally dissolved. And the change in colligative properties would be much, much greater than the amount of colligative properties changed by that little bitty amount of sodium chloride that does disassociate. Another thing to watch out for is when the identity of the molecule also can affect vapor pressure. So here's an example where you take glycerol, which basically has no vapor pressure. So when you put it in solution with water, very little vapor from glycerol comes up into the headspace. So the vapor pressure is predominantly created by water. This does affect the vapor pressure of water, and we'll talk about the exact numbers of it, as I showed you earlier in this demonstration. But comparatively speaking, if you put something like methanol in solution with water, methanol itself also has a vapor pressure. Now the actual partial vapor pressure of water in both cases will be the same, but you will have the added vapor pressure from the methanol, which also has a high vapor pressure. So when it's in solution, the total vapor pressure may increase. So you do have to pay attention to the identity of what you're putting in to change the solute properties if you're worried about changing the vapor pressure. And if you don't want to influence the vapor pressure with the solute itself, then choose a solute that has a low vapor pressure. An example of that, it's easy to find by checking the boiling point. Just for this example, the boiling point of glycerol is 290 C, whereas the boiling point of methanol is below water. Another thing to look out for is gases. When you take a gas and dissolve it into water, it may not dissolve in the traditional way like a salt. You're forcing it in there with pressure. An example that we're familiar with is carbon dioxide. Whenever you look at a Coca-Cola or any of the sodas, you basically have pushed carbon dioxide gas into solution by pressure alone. There's very little intermolecular interaction. And in this case, that has minimal effect on the colligative properties. So in the case where you take a gas that has little interaction with the solvent, there's little change on the colligative properties. But if you were to take a gas, as we talked about earlier, methanol is actually very polar, so it could bond to the water. And so if I introduce this methanol as a gas, it could also go into solution, but in this case it'll interact with the water and it will influence the colligative properties. So pay attention if you're talking about gases going into solution as to whether they're nonpolar gases. Then they're probably going to have very little interaction with the solvent. Unless, of course, the solvent is also nonpolar, and remember that idea that like dissolves like. What are some ways to get solutes into solution? This is just more practical advice of how we want to dissolve the salts. Temperature always affects solubility when it comes to solids, i.e. you're dissolving salt in water, or you're taking a polar material like sugar and you're dissolving in water. It is more soluble at higher temperature. Gases, on the other hand, become less soluble as temperature increases. And that has to do with the weaker association. So as you start to increase the temperature, you're actually increasing the kinetic energy, and it's easier for the gas to come back out of solution. And when it comes to pressure, it affects the solubility of gas, has very little influence on the solubility of a solid, but it's very important to the story of getting the gas into solution. And as you increase the pressure, gases become more soluble. Now here's an interesting study where we look at a large set of salts that have been dissolved in water. And generally speaking, every one of these trends, as you increase the temperature, you make it more soluble. So this is solubility going up the y-axis. So if you heat it up, you can get more in there. So as you increase the temperature, you can get all of these into solution. I just want to point out a couple anomalies on these graphs for you to understand. One of those is right here when we're putting calcium chloride in water. As we start off, it starts off as the calcium chloride hexahydrate, and then there's actually a change in the solid form to calcium chloride tetrahydrate, and that change in the solid form is why the line changes, and there's usually an up and down hump in these sorts of things. That happens again here where we have sodium sulfate, it's decahydrate, and then there's a change to where it's actually just sodium sulfate that's dissolving. And then there's one other little trend on here I'd like to point out, and that is cerium sulfate, nonahydrate. That particular material has an inverted trend line where it's easier to dissolve the cerium sulfate by cooling it off, and that's very unusual. And then another thing I'd point out is if you look at sodium chloride, when you look at the thermodynamics of dissolving sodium chloride, the bond breaking, bond forming events, it's kind of a wash, and consequently changing temperature has very little influence on the solubility of sodium chloride. And then getting back to this exception, that's probably easiest to explain why that happens in terms of entropy, and we'll save that for a later discussion. But for now, just know there are some exceptions to the rule. But generally speaking, this is what's most important for you to learn. As you increase the heat, you can increase the solubility, and the hand-waving logic there is that you're probably making it easier to break the lattice apart. This is a pretty straightforward trend. As you increase the pressure, you're actually pushing these gas molecules into solution. As the pressure increases, you have more molecules in solution. And this is once again how we pressurize CO2 into our soda pop. So I hope this has helped you understand just the colligative properties are and how things go into solution. And in the next video, we'll get into the more specific quantitative aspects of solutions.